questions on the homework real quickly? Okay, so what exactly would the formula for 10 through 12 be, at least for the starting portion?
Okay, 10 through 12. Okay, I'm gonna throw out 10. I meant to do it before. Okay, rectangular swimming pool. So you're just gonna assume that the swimming pool is like a box, uniform depth. Oh, and then a cylindrical barrel. Okay, I'll tell you. I wanted to say something about number 5. But let's wait until class starts, which will be in 1 minute. Okay.
Okay, so we don't have to worry about number 10?
Yeah.
Okay, thank you.
Okay, it's 8 o'clock.
Hey.
Time to start. Yeah, let's talk about the homework.
Miss Kennedy?
Yeah.
I also had a thing. Number 2, part C. I'm having some trouble with that one due to the 3x at the end. I'm not sure if I'm just missing it in the notes or not.
Well, the derivative of 3x with respect to x is just 3.
No. I mean, C is 2 square root of x plus y square root 3x.
So
the number would be 3. 3 for that.
Well, you take the derivative of the left-hand side and you set it equal to the derivative of the right-hand side. The derivative of the right-hand side is just 3.
All right. Okay.
Okay, and then y is the function, so that's, you have to use a chain rule on the square root of y. Okay, but let's see.
All right, thank you for
Let
that.
me talk a little bit about the homework. Okay, I'm going to share my screen. Okay. And all right. Okay, we're going to talk about the mean value theorem today, but let me just say some stuff about the homework first. In fact, let me just put another thing here. Okay. Yeah. In problems 4 through 6, it says in the next 3 problems. Oh, right. Okay. 4 through 6. Says to use the position function S of t is equal to minus 16t squared plus v0t plus s0. And that works fine for 4 and 6 because this is for the English system. That is, you're measuring things in feet per second and so forth, okay? But for problem 5, so for 4 and 6, this position function works fine. For problem 5, now that's given in terms of meters per second and meters. So the position function should change to this. Okay, and somebody wants in. All right, so let me, no, that's not the right one. Okay. All right, there. Okay, yeah, and the reason in the English system, okay, acceleration due to gravity is equal to 32 feet per second. So feet per second squared. And then that's your second derivative, and you get from that, you get your first derivative. From that, you get your function. Okay. And I don't want to go into all that yet, but somebody else needs in. Okay. Okay. Yeah, and in the oh no, that should be 4.9. Sorry, 9.8. In the metric system, it's 9.8 meters per second squared. So, in fact, that should not be 9.8. It should be minus 4.9. Okay, so make that change. S at t is minus 4.9 t squared plus V0t plus S0 for problem number 5. Throw out problem number 10. I don't know. That problem's always bothered me, and I've always meant to throw it out, but I left it in. Mr. Miller was...
So we can just skip problem number 10?
Yes. Mr. Miller has asked me whether that will be 80 centimeters squared per hour, which would be the surface area decreasing, or should it be 80 centimeters cubed per hour? Well, I don't know. I guess it's not real clear. And also it says the cubical box with a length of 15 centimeters is covered with ice of uniform thickness. So what happens at the edges? So I assume that with the ice, it's still a cubical box. I don't know. I just don't like it. So throw out number 10. Okay. Yeah. And there's, yeah, so that's one less problem we have to work. Okay. Any more questions about that?
Number 7, the tangent line. I can't find when we worked that.
We did it a while back, and there was also a problem like that on the practice exam for exam 1. Look back over it. Okay.
That's just it. I've been having trouble figuring out when, but if it was before exam 1 that we had an example of this, then I'll head back there and see if I can't find it.
Yeah. In fact, the reason it's on this homework is because I haven't given any problems like that before. Okay.
I think when I
Alright,
went
thank
to
you.
look for it, I want to say it was either back on September 2nd or September 3rd, sometime around then when we discussed it.
Okay, thank you. So September 2nd or September 3rd. Okay, remember you have a exam 2 coming up next Friday. Okay. It will cover the October 2nd homework that you're handing in today, and also the September 25th homework. And it will not go beyond that material. So related rates is the last thing that will be on your exam. Yeah, which means that what I've been talking about yesterday in particular will not be on the exam, and what I'm going to be talking about today will not be on the exam. It'll be on the next exam. Okay, I do want this. Okay, I want that. All right. Okay. So we talked about, let's see, Rolle's theorem is a preliminary thing to the mean value theorem. The mean value theorem.
Wait, what about for questions 11 and 12?
Oh, what about them? Oh, well, a rectangular swimming pool. Okay. So the volume of the swimming pool is given, and the water is given by the length times the width times the height. It's a box, basically. Only this box, if you're talking about the water in the box is changing. It's the water level's decreasing. Okay, so the basic model for the swimming pool, let me go back. All right. Okay, for 11, you're assuming that the swimming pool that the volume is length times width times height. The length and the width don't change, but the height does. Okay. The length is 25 feet and the height, no, the width. The width is 20 feet. And I will leave the rest to you. In number 12, rain is falling into a cylindrical barrel. Well, what's the volume of a cylinder? It's pi r squared h. And I'll leave the rest to you. Okay, so, and there's also 13 and 14. Don't miss those. Okay.
So could the part that is asking for the rate of change in the height be used in replacement of the h value?
Yeah.
Okay, thank you.
Okay. Yeah. Okay. No, that's not what I wanted to do. Okay, let's go back. There we go. Okay. The mean value theorem. Yeah, Rolle's theorem is, well, if you can prove Rolle's theorem, you can prove the mean value theorem. But it's the kind of the third one of these big theorems. We had the intermediate value theorem, the extreme value theorem, and now we're going to get the mean value theorem. The mean value theorem, it's hard to get students to appreciate how important this is because you have no frame of reference for it. Once you take higher levels of mathematics, in particular something called analysis, you see the mean value theorem coming up over and over and over again. But right now, okay, it's hard to give good problems on it even, but it matters. So, okay, let's talk about Rolle's theorem. It says you have a function, and this function is continuous on a closed interval. And okay, it's differentiable on the open interval. Okay, it's continuous on the closed interval from A to B. So that includes A and B, the two endpoints. You only require that it be differentiable on the open interval. So everything except maybe at A and B. And also f of A is equal to f of B. Then there must exist the number C in AB such that f prime of C is 0. Okay, we're actually going to prove this. But kind of let me draw you a picture. Suppose that's A and that's B. And we're assuming f of A is equal to f of B. So that's the same height. Okay, well, it could do a lot of things. The function could do a lot of things, but oh, say it does something like that. Well, f prime of C is equal to 0. Okay, you're going to have, that's the slope of the tangent line is 0. And it looks like that's such a C and that's such a C. Okay. Also, the extreme value theorem and the intermediate value theorem only assumed continuity on a closed interval. This one now we have a condition on, well, it's got to have a derivative for the points inside the interval. Okay, but let's prove this. There are 3 cases to consider. And one, okay, the function could be a constant function. So, well, that means the graph is something, it's a horizontal line. All right. Well, then we know that for a constant function, f prime is 0 for each x. Well, in the open interval AB. So it's true. Okay, so you could take any x in the open interval from A to B to be that number C that we're trying to prove exists. Okay, so that was easy. I didn't finish writing that. I'll write it later. Okay. In the second case, f of x is greater than f of A for some x in AB. Okay, so that's A and B. I'm assuming that f of A is equal to f of B. But now I'm also assuming that f of x is bigger than f of A for some x in AB. So it pops up above the level of f of A someplace. Okay, well, we can use the extreme value theorem. We have a continuous function defined on a closed interval, and the extreme value theorem says we're guaranteed an absolute maximum and an absolute minimum. In particular, we're guaranteed an absolute maximum. Okay, so we get the fact that we have an absolute maximum in there. And let's see. So there is some point C in the open interval from A to B. Remember, f of A is equal to f of B, and there is some x such that f of x is greater than f of A. That x doesn't necessarily have to be where the maximum occurs, but there does have to be a place where the maximum occurs. Oh, somebody came. Okay, let me go to let somebody in. All right, there. There's some point C in A B such that f of C is greater than or equal to f of x for each x in the interval, and that's got to be, well, it's an absolute maximum, but it's also a local maximum. And by Fermat's theorem, okay, and what did Fermat's theorem said? It said that if you have a local maximum or minimum at a number C and f prime exists, then f prime of C is equal to 0. Okay. Well, f prime of C exists by our assumption. It's a local maximum, so f prime of C has to be equal to 0. Okay, so in the first case, f of x was equal to the same number for every k. In the second case, the graph popped up above f of a someplace. And the third case, we'll suppose for some x in AB, f of x is less than f of A, which is equal to f of B. Well, this is very similar to what we just did. Okay, pretty much the same proof. Again, we can use the extreme value theorem to conclude that f has a minimum value on AB, and the minimum value is not f of A because there's some x in AB such that f of x is less than f of A. Okay, so there is some C in the open interval from A to B such that f of c is less than or equal to f of x for each x in a b. Well, f of c is an absolute minimum, but it's also a local minimum. And by Fermat's theorem, again, since f prime of c does exist, f prime of c is equal to 0. Okay, so that proves it. And there are only three cases possible. Either f of x is constant on the interval, or it's bigger than f of a someplace, or it's less than f of a someplace. And okay, it could be both greater and less, such as in that picture. Okay. Both cases 2 and 3 would apply here, but that's all right. I have considered every possibility. So that ends the proof. Any questions? Well, I won't make you listen to a proof of the mean value theorem, but let's just state it, and I'll tell you why it's true. Actually, once you know Rolle's theorem, it's not hard. The mean value theorem, or MVT, okay, that says the same hypotheses, except for the f of a equal to f of b. Suppose that if satisfies the following. One, f is continuous on the closed interval AB, and 2, f is differentiable on the open interval from A to B. Okay, and this time I'm not going to assume that f of A is equal to f of B. But then there is a number C in AB such that f prime of C is equal to f of B minus f of A over B minus A. Okay, what does that say? Equivalently, f prime of C times B minus A. That's true. Okay. F of A and f of B, and suppose f looks like that. Okay. All right. Well, what is this number? F of B minus f of A over B minus A. Stop that. This point is A f of A. this point is b f of b. F of b minus f of a over by b minus a is the slope of the line through the points a f of a and b f of b. Okay. So, okay, let's draw the line through those 2 points. That red line. Okay. So this number is the slope of that red line. And the mean value theorem says for some number C that's strictly between A and B, F prime of C is equal to the slope of that red line. Okay. And sort of, okay, just a picture, but it looks like maybe it would be, say, right there. There is some number C, so this would be C. The slope of the tangent line at C then is the same as the slope of the red line. That's what the mean value theorem says. And, okay, once you know Rolle's theorem, it's easy to prove. All you do is basically take your function f and subtract the function determined by the red line. So you apply Rolle's theorem to f of x minus L of x, where L of x is the line through A f of A and B f of B. Because then once you do that, you've got, for this new function, now you've got g of x, g of A is equal to g of B, and you can apply Rolle's theorem. But okay, I will not subject you to that. Let's work a problem. Okay. Again, this is a theoretical result, and it's really important to the whole underpinning of calculus. This little theorem. It's really hard to get you to see that because you have no context for seeing it. So, okay, we'll just work a few problems, but maybe you'll take my word for it that it's important. If you take something called analysis, you'll see for yourself. Okay, so let's see. Let's apply these. Questions before I go forward? No? Okay. Let's prove that the equation x cubed plus x minus 1 equal to 0 has exactly one root. Okay, so that means it's got a root, but it doesn't have two. So let's break it up. first show that it has at least one root. And actually, okay, this means we're going to use the intermediate value theorem. For that part, if I can find an x such that f of that x is positive and another number y such that f of y is negative, that'll do it for me. Okay, so let's look at f of 1 would be equal to 1 plus 1 minus 1 is plus 1, and that's greater than 0. F of 0, on the other hand, would be 0 plus 0 minus 1 is minus 1, then that's less than 0. Okay, so the intermediate value theorem implies that there is some number C in the interval from 0 to 1 such that f of little c is 0. F of 1, let's see, draw a picture. F of 1 was 1. No, that's wrong. Okay. F of 1 was 1. Call that 1. F of 0 was minus 1. So that point's on the graph, that point's on the graph. And the intermediate value theorem says that the graph has to go through 0 then. To get from minus 1 up to 1, it's got to pass through 0. Okay. Well, that says there's at least one number such that that's true. But what if the graph does something like that and it's got like maybe 3 roots? Okay, so it could maybe have more than one. Okay, so but now we know. There's at least one number. I want to show that there's not another one. Okay. But I've got some progress here. There's at least one root. So the second thing, I want to show that C is the only. My pen's not writing. Okay, let me. There. Why it does this sometimes. No, I'm sorry. Okay, so we show that C is the only root. Well, okay, what I'm going to do to show this is, well, suppose there are 2. And prove that that can't happen. that there is some other number D in 0, 1 such that f of D is 0. Okay, so we have f of C is 0 is f of D, and we're assuming too that C is not equal to D. Well, if that's true, okay, did I ever? No, I never said what f was. F of x is x plus 1. I'm sorry, I should have written that the first. Okay. Okay. All right, but this is a cubic polynomial, so it's continuous over all the real numbers. But in particular, it's continuous on the interval from 0 to 1. Ah. Okay. So, no, I want more than that, don't I? Okay, let me see. Yeah, I don't want to make that assumption. Just some number D. So I don't care whether it's between 0 and 1 or not. All right, but there is a closed interval. I'll call it A prime, B prime, that contains 0, 1, C, and D. In fact, if it contains 0 and 1, it's got to contain C, but I don't know where D is. Okay. There's a closed interval such, yeah. And F is continuous on that closed interval because it's continuous on all the real numbers. F is differentiable on the open part of that because it's differentiable everywhere. Okay. And F of 0. Oh, no. F of C is equal to F of D. Okay. All right. So actually, I only need it to have for it to contain C and D. But I don't know which one, whether C is less than D or D is less than C. So I'll just, okay. So, okay. I'm going to write that. So that would say that C is less than D. If in the other case, it would be from D to C. It's the same proof. In fact, I could just say, let C be the smaller of the two numbers. That would take care of it. Okay. But this is the interval one. It's continuous on CD. It's differentiable on the open interval, and F of C is equal to F of D. So by Rolle's theorem, or the mean value theorem, there is some, I've already used C and D. Okay, I need to name it something else. Some number S in CD such that f prime of S is equal to 0. Okay. So Rolle's theorem says that this has got to be true if I've got two places where f of C is equal to f of D, which is equal to 0, right? But what is f prime equal to? F of x is equal to x cubed plus x minus 1
If I do call, it will be equal to 3x squared plus 1.
Right. Okay, so this is my function. That's the derivative of that function. And notice 3x squared plus 1, well, that's always greater than or equal to 1. For every x. For every x, that's true. So this cannot possibly be true. Okay. And yeah, so then f prime of s equal to 0, some s. Can't be true. You've reached a contradiction. Okay, so that means my assumption must have been wrong. And what was my assumption? That there was another number. We know that we got this one number C, that's the root. We were assuming that we supposed we had two different numbers such that f of C was 0, f of D was 0. But that leads you to the conclusion that f prime has to be 0 someplace, and it's not. So this is a contradiction. And no such number D exists. A C is the one and only root of that function, which was 3x. No, which was, that's the derivative. Okay. X cubed plus x minus 1. Okay. Let's do any questions. What time is it? 48. It's getting pretty late. Yeah, do you have any questions about that? Let me do one more quick problem. Okay, so this is for the mean value theorem. Suppose that f of x is equal to 3x squared plus 2x plus 5. And we want to consider the interval from -1 to 1. Okay, so what do we want to do? Verify that the hypotheses of the mean value theorem are satisfied. And then find all numbers C in -1 to 1 that satisfy the conclusion. Okay, the mean value theorem, the intermediate value theorem, and the extreme value theorem, they all are existence theorems. And okay, for mathematicians, this is really important. Okay, something that guarantees the existence of something. It does, but they don't tell you a thing about how you go about finding that thing. But okay, so engineers and whatever, they take exception. They want to know what that number C is. But at least if you know that the number C exists, it makes sense to look for it. For this problem, we can find it though. Okay, verify that the hypotheses of the mean value theorem are satisfied. Okay, well, those hypotheses were f is continuous on the interval -1 to 1, check, because it's a polynomial. And the second one was that f is differentiable, abbreviate, on the open interval from -1 to 1. Check, it's a polynomial. It's kind of continuous and differentiable everywhere. Okay, so we're done with that. Well, then the mean value theorem says that there is some number C in -1 to 1 such that f prime of C is equal to, okay, f of B minus f of A over B minus A. Well, what's B is 1 and A is -1. That's f of 1 minus f of -1 over 1 minus -1. What's f of 1? Let's see. F of 1 would be 3 plus 2 be 10. F of -1 would be 3 minus 2 plus 5 is 6. Over 2, which was 4 over 2, which was 2. Okay, so f prime of C must be equal to 2. And well, I can figure out what f prime is pretty easily. F was 3x squared plus 2x plus 5. So f prime is 6x plus 2. And that means that f prime of C is 6c plus 2, and it's also equal to 2. Okay, so 6c is 0, and c is 0. And that does it. Well, there's only one place. In fact, this is a parabola, so there can only be one place. But it's actually probably the now I have to draw the picture. Okay. Well, I'm out of time. Anyway, so yeah, on Monday we will do another one of these problems and kind of go over it one more time.
Slow down a little bit more.
What? Okay. Somebody said something.
Yeah, I was trying to write your conclusion.
Oh, you want me to go back to the shared screen?
Please.
Okay. Class is over, so you all can leave, but I will go back to the shared screen.